In this module, we will be looking at a system that relates to sensation. That is not just limited to touch, but also to pressure, pain, or temperature. And this can occur anywhere in the body. Some individuals believe that we, as humans, do not have just 5 senses. The sense of touch can be expanded onto various others, as again, there is pressure, pain, warmth, that can all occur within the body in contrast to just one localized at a sense organ. Somatosensations occur anywhere in the body and are broken up into 3 major systems: exteroreceptive, interoceptive, and proprioceptive. Exteroreceptive is basically activated when there are stimuli that are external to the body of an individual. If it's hot outside, then we start feeling the temperature ourselves, and there would then be physiological changes for your body to start sweating, but this would be in response to something that's external to the organism. Interoceptive, the contrary, is stimuli that's produced and perceived within the organism. So if the individual has a fever, and that is because of an infection within, regardless of the temperature outside, there would then be physiological change because of the stimuli produced and perceived within the organism. Proprioceptive is the third somatosensory system, and while the definition is very similar to interoceptive, please note that proprioceptive is pertaining to the position, movement, or acceleration of the body. The proprioceptive test is done typically by police officers using the field sobriety test. They may ask the subject to touch his or her nose with their eyes closed. People with normal proprioception may take an error of no more than 20 millimeters, while people suffering from impaired proprioception, which would be a symptom of moderate to severe alcohol intoxication, would fail this test because of the difficulty in locating their limbs in space relative to their noses. Please note that proprioceptive has been used to diagnose individuals who may have visual and tactile placing reflexes and deficits with that. It's also what allows individuals to learn to walk in complete darkness without losing balance. During the learning of this new skill or sport or art, it is usually necessary to become familiar with some proprioceptive tasks that are specific to that activity. Without that specific integration of proprioceptive input, an athlete or an artist would not be able to locate and their body or their footing to get something. It would be impossible to drive an automobile because a motorist would not be able to steer or use pedals while looking at the road ahead. A person could also not touch, type, or perform ballet, and people will not be able to walk without watching where they put their feet. So please note that proprioceptive has various applications, and it is, some people argue, a little bit more difficult perhaps than exteroceptive, which is simply a response to environmental things. To detect things, whether it be exteroceptive or interoceptive or proprioceptive, we make use of cutaneous receptors, which are sensory receptors that are found in the dermis or epidermis. Dermis, you may know that it is the under part of the skin. It is subdermal here. The epidermis would be above, and it would be directly at this specific area here. Here we're going to look at a few of the cutaneous receptors, and the first one we'll look at is the free nerve endings, which respond to temperature and pain. You can see that these are located closer to the surface, and they look like dendrites as they have branch-like things that would respond again to temperature changes and pain. The Pacinian corpuscles, these are deep, buried a little deeper in, and they actually have a circular form. You can see them on the right side of the screen. These particular receptors are known for their quick adaptation, but they're also known for responding to sudden displacement of the skin. But because they adapt quickly, they would not constantly trigger a response, because they don't do so with constant pressure. Think of perhaps putting on a pair of socks in the morning before going to school, and you would see that initially you would probably feel the socks, but throughout the day you would not. And the reason why is because the Pacinian corpuscles have adapted rapidly to the presence of that stimulus, and they do not send a signal over to the brain to alert you that you have socks on. The Merkel's disc, or Merkel's as some people also pronounce, respond to gradual pressure. And so when we look at gradual pressure, we're talking about skin indentation. If you've ever worn a pair of socks that are too tight, you may not feel anything until after a period of time. In fact, some individuals do not feel anything until the end of the day when they get home and remove them, and then they're able to see that their skin has been indented because of the constant pressure. This responds again to gradual pressure, but they do not have a quick response to it unless it's severe. And the Ruffini endings, which are over here, these Ruffini endings are the ones that are also known for responding to gradual skin stretching. And the skin stretches to various responses. If you do the obvious, like an Indian burn on someone's arm, then that would be one form of stretching the skin. But we also know that when we get cold, if you've ever experienced cold temperatures, and we know that for Californians and Angelinos, it is anything below 70 degrees, but we're talking about maybe 20 degrees or 30 degrees. If you're outside for a while with a wind chill factor, you see that your face may, if it's not covered, would start feeling stretched and very dry. And it would actually be an activation of the Ruffini endings that are sending a message over to your brain so that something could be done about it. Please note that these cutaneous receptors constantly require that you have blood pump in there. If you do not have blood, then these would also die, and they would not be helpful anymore in sending messages to the brain that would keep you safe or alive. We used to think that each type of receptor was responsible for mediating different tactile sensation. So we thought that perhaps one of these was responsible for temperature, and the other one was responsible for pain, and the other one was responsible for caressing, and we now know that that's not the case. In fact, we know that our ability to recognize things and our ability to perceive objects just by touch, which is what we call stereognosis, relies heavily on the work that's done collectively by various receptor mechanisms. Stereognosis, again, is our ability to perceive and recognize a form of an object just simply by the touch. We may give an individual that's blindfolded perhaps a pencil. We may give him a water bottle, and based on the size, the texture, the spatial properties, the temperature, the individual with functional cutaneous receptors would be able to determine what that specific object is. Stereognosis tests determine whether or not the parietal lobe of the brain is intact. And the reason why is because that is where we are processing the information from our fingers. Typically, these stereognosis tests are involved having the patient identify the most common objects like perhaps keys or comb or safety pins. These are placed in their hand without any visual cues, and we find that the stereognosis is a higher cerebroassociative cortical function. And that is why we know, again, that it is at the parietal lobe. Once we get our cutaneous receptors to fire, there are neural fibers that carry the information over to somatosensory receptors into the specific spinal cord and eventually to the brain. Here you can see a layout of how the information would be mapped out in a way that is easily located and allows us to understand the body and the brain and the spinal cord better. You may notice here that the body is set up with specific codes in here. So you have L2 for the left thigh of the individual. Any cutaneous receptors in here that would sense specific form of stimulus, whether it be temperature or pain, it would then activate the receptive cells, and it would then over-innervate to the corresponding area of the spinal cord. In this case, it would be at the lumbar vertebrae area, L2. Notice that if you have some type of accident where you step on a Lego and step on it with the heel of your foot, it would then be the S1 on the left side. It would then over-innervate through the back of the spine at this specific area here. Same thing here. You have a C5, something happened to your arm, and then you'd be able to then innervate over to the cervical vertebrae area over here. Please note that the gathering or the innervation of the nerves from the PNS to the spinal cord always enter through the dorsal part. They always enter through the back. From there, it would then be sent over to the top of our head, and then your brain would decide what to do about that specific sensation. Dermatome is basically an area of the body or the skin that's innervated by the left and right dorsal roots of a given segment of the spinal cord. And so again, please keep in mind that depending on what you're feeling, what side of the body you're feeling, it would then be synapsing or innervating, connecting to the respective area of the spinal cord. Left would go to the left side of your body would go to the right side of the spine, and the right side of your body would go over to the left side of the spine. Once our cutaneous receptors in specific parts of their body innervate to the respective areas of the spine, they send a message upward from the dorsal part of the spine to the brain. And where they go, specifically, is at what we call the cortical area of somatosensation. You can see in here that the cortical area, the primary somatosensory area, would be this purple part right here. And it is procentral to the central fissure, meaning toward the posterior part of the central fissure. The secondary somatosensory cortex would be the smaller area here. You may notice and remember back from the occipital lobe where the primary was here and the secondary was larger. Same thing with auditory. The primary was smaller and then the parabelt was larger. Well, here we see the opposite. The primary is actually larger and then the secondary is much smaller. If we do a cut and we would look at the layout of our respective body parts, the locations of the human primary somatosensory cortex within the conventional portrayal of the somatosensory cortex here. You can see that closer to the central fissure, we would see that this part would pertain to any sensation, stimulation of the genital area. Right above that, we would see the toes and the foot, which would be somewhat similar, interesting to see because you may remember that the parts of our heel and our genitals actually innervate to the sacral vertebrae part, which is the lower part of our spine. So it is laid out in a very organized fashion. From there you see that the leg, which regardless of its large size with the hip and trunk, they only occupy a small part of the cortical area of somatosensation. Then we get over to the elbow, forearm, wrist, and then when we get to the hand, notice how the hand occupies a very large part of our cortical area. This is because of the dexterity. The neural fibers that basically carry information that is a lot more functional, such as a hand, which you could do so many things with, requires a lot more cortical area. The face is something I want us to look at in here because prior to the 90s, we used to think that the face was this way. Now we actually believe, and the arrow is a little bit off in here, but now we believe that it's the other way around. Ignore this arrow here, and instead I want you to make it upside down. So whereas the eyes would be over here, the nose would be over here, the face would stay there, the upper lip would be where the nose is, and the lower lip would be where the eye is. This, again, was supported by results of an fMRI study that we find that the face representation is also inverted, similar to the rest of the body. And just like that, we were able to locate our entire part of our body in relation to the spinal cord and to the cutaneous receptors. The rubber hand illusion is a fascinating study that has led to the understanding of how our brain works in relation to the peripheral system and also our body. The rubber hand illusion basically consists of constantly stroking a rubber hand that is visually aligned with the individual, the participant. Meanwhile, the participant's actual hand is out of sight, blocked by a cardboard box typically. The researcher here would be stroking and stimulating the hand in a similar fashion. And in less than a minute, volunteers typically begin to feel that the rubber hand being touched when their hidden hand is being touched. In other words, the rubber hand, they begin to integrate it into their own body. The hidden hand, interestingly, begins to drop in temperature as soon as the rubber hand is incorporated, which is typically within a minute. So after just stimulating this for a minute, it seems that our brain begins to neglect our actual body part and says, well, there's no need for me to be pumping blood there because I am getting tricked a little bit. Functional imaging studies has suggested that association cortex of the posterior parietal lobe, which is somatosensation, and the frontal lobe play a role in the rubber hand illusion. It's also been suggested that bimodal neurons with both visual and somatosensory fields play a critical role in this. Please note that covering the participant's eyes when asked to point their hand, they will actually point with the other hand to the rubber hand instead of their own. This is a very interesting study, and I'll show you a video at the end of this slide and a separate link that would show you how this generates fear with individuals based on what the researcher does to them. The pharmaceutical industry makes a lot of money generating medicine, creating medicine to control pain. Despite its unpleasantness, pain is an adaptive and a needed component for survival. Painful stimuli activates many areas of the cortex, but the particular areas of activation vary from study to study and from person to person. And the reason why is because we believe that pain is a perceptual response, meaning that if you're cognitively not well, and perhaps you are depressed, you are more likely to perceive the pain as more intense than if you were to be well. We find that although there are parts of the body that in our brain that are controlling specific parts of the body, none of these areas are necessary for perception of pain. In a study that was done in 2008 by Schul, painful stimuli usually elicits response in the somatosensory area 1 and somatosensory 2. However, the removal of these areas in humans is not associated with any change in the threshold of pain. We find that these individuals who would have gone through this procedure of removing these specific areas, they would still perceive pain from both sides of their bodies. You may have read the very interesting case study in our textbook of Miss C, a student at McGill University in Montreal. She was very intelligent and was normal in every way except that she never felt pain. She felt no pain when subjected to strong electric shocks, burning hot water, or ice bath. Equally astonishing was the fact that she showed no changes in blood pressure, heart rate, and respiration when these stimuli were presented. Furthermore, she did not sneeze, cough, or display corneal reflexes, such as blinking to protect the eyes. As a child, she had bitten off the tip of her tongue while chewing food and had suffered severe burns while kneeling on a radiator. Miss C exhibited pathological changes on her knees, hip, and spine because of her lack of protection of joints provided by pain sensation. She apparently failed to shift her weight when standing to turn over her sleep or avoid harmful postures. Miss C died at the age of 29 of massive infections and extensive skin and bone trauma. As stated earlier, the perception of pain is adaptive and, despite its unpleasantness, is necessary for survival. To understand how we perceive pain, we look at what's known as the descending pain control, and this It's basically pain that can be suppressed by cognitive and emotional factors. This is what we call the gateway control theory. So when we look at the gate control theory, we equate our body as a gate, and if we expose it to something painful, then we would open the gate and we would sense and experience pain. However, we believe that it is possible that you and I could reduce that discomfort or completely eliminate it simply by our cognition and emotional factors. Different studies have suggested that individuals who go to war and come back with a particular injury to their body, in some cases the amputation of a limb, if they feel that the war was for a good cause, they tend to consume fewer pain medication and also report less discomfort. Individuals who feel that the war was a crime and done for private interest and only for perhaps greedy agendas, these individuals tend to have a negative attitude about war, about the government, and they also consume more pain control medication. This would lead to the understanding of the emotional factor being associated with pain. Cognition, we actually understand that if the individual believes that the pain is going to be permanent and it will never go away, then they would have a more pessimist attitude about what would be coming, and the individual is likely to intensify the sensation of pain. But if the individual recognizes that the discomfort is temporary and that after this time they'll be back on their feet, then the individual tends to experience a less intense sensation. You may have heard that the mind is a powerful thing. This is evidence that such is the case. And we've in fact found gender differences where it is indicated that women tend to adapt better to pain than men. In fact, it is quite interesting to see how a woman goes from extreme pain while giving birth to having completely forgotten about the pain as soon as she's holding her child in her arms. Again, looking at the cognitive and emotional factors influencing our sensation of pain. Here you can appreciate the circuitry of the descending pain control pathway. This circuitry was identified in the 1970s, and some of the most important findings in here is that the electrical stimulation of the PAG area, the periaqueductal gray area, which is located here, actually brought about analgesic effects, meaning the individuals would feel a sense of numbness that would keep them from experiencing pain. The periaqueductal gray area and other brain areas are known to have opiate receptors, and these opiate receptors are receptive to drugs that are created by the psychopharmacologists, by pharmacists, that would allow the individual to reduce pain if necessary. We also know of the existence of endogenous opiates, and these are basically natural analgesics, endorphins. And our endorphins, which are produced by your body naturally, are affected by your emotions. Going back to the theory that we looked at earlier, the gate control theory of pain, which allows individuals to sustain and to withhold and to tolerate pain more so, depending on their emotions. In fact, there are various studies of individuals who are able to go through torture for religious reasons or for whatever other reason, simply by controlling their emotions.